Hello, everybody. We're going to continue our conversation about the ISM, that's the interstellar medium. And this video is all about the crowd-pleasing parts of the ISM nebulae. So let's go ahead and dive right in. I have this presentation set up as an introduction to what nebulae are, then going through the different types of nebulae, and ending with just a series of pictures of nebulae that exist out there in outer space. This is where a lot of the prettiest pictures of outer space come from. So just starting this conversation about nebulae, here we have the Seagull Nebula, which is an emission nebula. And you can see that there is a bunch of red light that's being emitted by this cloud of mostly hydrogen gas. The red light is mostly hydrogen alpha light. That's a wavelength of 656.3 nanometers. But once you mix in hydrogen beta and the other hydrogen emission lines, it doesn't look pure red. It sort of looks like a pink color. And remember, I have mentioned in the past that when the eye sees pink, you can think of pink as the color of not green, because when your eye, the little detectors in your eye, we can sense red, green, and blue. Whenever we get detections in the red, when we get detections in the blue, our brain interprets it as pink. And hydrogen alpha is red, and that's going to be the brightest component of this. Hydrogen beta is blue, and then hydrogen gamma, so on and so forth, are also blue. So here is an emission nebula, absolutely stunning views of outer space. And you can even see some dust clouds over here. So let's just go ahead and get in and talk about what a nebula is. So there is nebula, which the plural of nebula is nebulae. That's with an AE at the end. And really, just in the most nebulous definition of the term nebula, sorry, I had to do that. It's a collection of gas and dust in outer space. So any collection of gas and dust in outer space, and by collection, I mean it's going to be collecting together so it's more dense than just the surrounding interstellar medium that is better than the vacuums we have here on the Earth. But a nebula is just a collection of gas and dust in outer space. They are the higher density phases of the ISM, and that means that we can visually see them, whether we can see them because of the dust blocking the view of light, like these dust lanes in the Milky and near the core of the Milky Way, or you can see them because they are emitting their own light, like the Lagoon Nebula here at M8, or the emission nebula up here in the Trifid Nebula, or perhaps we're seeing reflected light, this reflection nebula above the Trifid Nebula. And here you can see them in context within the Milky Way. So these are all collections of gas and dust in outer space. So these are all nebulae, and there are several different types of nebulae. And we're going to go over each one of them. We're going to go over the primary types that we'll talk about in the interstellar medium. All of these lie in the interstellar medium, but here I'm going to introduce emission nebulae. They are emitting light. So here you can see that characteristic pink glow of an emission nebula, mostly from hydrogen alpha light. We have reflection nebulae, which are reflecting light. So you can see that blue part right there is a reflection nebula. It's reflecting the blue light of hot O and B type stars. And then we have dark nebulae and molecular clouds, which these are the densest regions where there's enough dust there and it's dense enough where it blocks the light that's coming through, so we can't see them and they appear dark. And I'd love to say that these are all, you can deal with each one of these in isolation, but you always have these are overlapping with one another. So you can't just say emission nebula, reflection nebula. Usually a nebula contains a nebula is a complex of various parts of the ISM, a collection of nebulae, and that has emission parts, reflection parts, and dark parts. And we'll see that as we go through, but it's good to break out the different parts into the clear parts where we have the emission part, the reflection part, and then dark nebulae and molecular clouds. Molecular clouds are their own beast. They are the densest, coldest regions of the ISM, and they are, at least for me, where the most action and most excitement is. These are not the only nebulae we see. We also have planetary nebulae. That's how a star like our sun, a low mass star, dies. That's one of the last stages of stellar life. And then we have supernova remnants, which is post supernova. All that gas and dust is still hanging around. And it's really, really highly energetic because, supernova explosion. And those are also nebulae. I'm not going to talk about them here in this part because we will get to those as we talk about the death of stars. So over here, I'm going to focus on the emission, reflection, dark, nebulae, and molecular clouds. Let's first take a look at the emission nebula. And what I'm going to do is I'm going to zoom in on the Trifid Nebula right here. So we'll zoom in on the Trifid Nebula, also known as Messier Object 20, M20. And here you can see that it is glowing this nice characteristic reddish pink color due to mostly hydrogen alpha emission. We are seeing the hydrogen emitting a lot of light, and therefore we call this an emission nebula. But you can also see that this red glowing part, that's the emission part. You can also see the dark nebulae, these dark dust lanes, and on top of it, you have a reflection nebula. But whenever I'm talking about the emission nebula part of this, the emission nebula is where it's glowing pink and emitting light. Why are these glowing pink? Why are they emitting light? Why are they emitting so much of this hydrogen emission lines? Well, it's because the hydrogen there is highly energetic. All of the emission nebula have at least one, sometimes more, embedded hot O and B type stars. These are the hottest stars that are out there. If you want to use Wien's law, it tells us that the peak of their blackbody spectrum is in the ultraviolet. So most of the light that they give off is ultraviolet radiation. That's the kind of radiation we need. We call that ionizing radiation because that's the kind of energies we need to ionize something like hydrogen. And it's the minimum amount of energy, ultraviolet light, to get electrons and hydrogen out of their ground state and into higher energy levels. So these hot embedded O and B type stars are getting all the electrons excited in the hydrogen, most of the time ionizing the hydrogen, removing the electrons, and then the electrons will cascade back down as they reattach to hydrogen atoms, going through all those different energy levels. And the most popular transition is from the second excited state to the first excited state and emit hydrogen alpha light, which we see as this nice red color. So that's why emission nebulae are glowing. They are emitting light according to the rules of spectroscopy that we talked about. And since the ISM is mostly hydrogen, we're really talking about the Balmer series here. So the red in color from this hydrogen alpha emission, Balmer alpha. And also, whenever we're talking about this phase of the ISM, whenever we're talking about emission nebulae, we're talking about hot hydrogen gas or hot gas. There's helium there as well. But the gas is about 10,000 Kelvin. That is an extraordinarily high temperature. So very, very hot gas. These are also emission nebulae are called H2 regions. That's the Roman numeral for 2. And we call them H2 regions because the hydrogen gas is primarily ionized. It's primarily ionized hydrogen. So we pronounce this H2, and H1 would mean non-ionized neutral hydrogen. H2 would mean singly ionized hydrogen. It's that's totally ionized for hydrogen. So we use the Roman numerals to talk about the ionization state. So H2 means ionized hydrogen. So whenever we talk about an H2 region, we're talking about ionized hydrogen regions. So if we want to know what the state of hydrogen is for an emission nebula, the correct answer is to say it's almost all ionized. There's not really neutral hydrogen laying around, except for whenever the electrons get back together, emit some light, but then they'll quickly get hit by an ultraviolet photon from the O and B type stars and get ionized once again. All right, so within this Trifid nebula complex, we can also see up above it this sort of glowing blue cloud. So this cloud is blue, not because it's emitting light, but because it's simply reflecting light from the embedded hot O or B type star. Being a hot star, it's a blue in color, visible light color. That light is going to hit the dust here in this region. It's far enough away where the intensity of light's not high enough to ionize the hydrogen anymore, but there's still plenty of dust particles that can scatter that light, and it's preferentially going to scatter blue light. So no matter what way you look at that nebula, you'll see the blue light being reflected back towards us. So these reflection nebulae, circled here, appear typically blue, sometimes white light. It depends on what kind of star, what kind of light is being reflected. And here we're talking about hydrogen gas that's atomic and neutral. So we're talking about hydrogen atoms, and they're neutral hydrogen atoms. They still have their electrons uh, associated with them. And so since this is neutral hydrogen, its ionization state would be Roman numeral 1. So we call these H1 regions. The hydrogen here is not ionized. We're dealing with lower temperatures, lower than 10,000 Kelvin. And these are also always associated. You need something nearby to reflect the light. So these are also going to be associated with our emission nebulae, which have those embedded OMB type stars. Now let's zoom out a little bit and take a look not only in the visible part of the electromagnetic spectrum, but the infrared part of the electromagnetic spectrum, and take a look at these dark nebulae, our third type that we're going to talk about. So here you can see these dust lanes that are going throughout the Trifid Nebula. In fact, that's why we call it the Trifid Nebula, because it divides it into sort of this section, 1/3, 2/3, 2/3, is trifurcated. So here we have our Trifid Nebula, and here we have our dark nebulae going by there. Why are they dark? Because while it's 99% gas in there, there's also a lot of dust, and these regions are denser than other regions. So there's a significant amount of dust there. So the light from the emission nebula can't penetrate through all the dust. The dust absorbs it. We have total extinction, so they appear dark in visible light. Here you can see some dark nebulae up here as well. So the dark nebulae are dark because of dust. Go back to my first video on the ISM, and you have the Barnard 68. That object, that is a dark nebula. So they're dark due to total extinction of light, to bring that term back. They are also extremely cold, since the dust is absorbing all the light, protecting the inner regions from ever getting really illuminated. Then they can cool down to very, very low temperatures, 50 Kelvin or less. And since they're so cold, they don't emit a whole lot of light. And they are actually quite hard to detect what kind of gas is there, because they are so cold, and neutral hydrogen gas that's cold doesn't emit a whole lot of light. So here the hydrogen is neutral again. It is H1 hydrogen, non-ionized hydrogen, neutral hydrogen. But here we're talking about hydrogen depending on the environment, depending on the nebula. It could be atomic hydrogen, just atoms of hydrogen, or if it gets cold enough, you can form molecular hydrogen, two hydrogen atoms bonded together. And what I absolutely love is switching from visible light to infrared light, where we can see the dust emitting light. It's cold dust, but it still emits some light. And since it's dust, all little bits of things, they approximate a black body. So they emit light like a black body, and they do a lot of that emission in the infrared, or the far part of the infrared, mid to far part of the infrared. So if we switch to that wavelength range, we can see the dust itself. So here's that same region, and now you can see all of the dust that's there. You can see the dust glowing. So in the infrared, dark nebulae are not dark. They're the bright things. So dark nebula is sort of a nebulous term. Man, I'm never going to get tired of that joke. So it includes everything like that Barnard 68 that we saw. It includes these dust lanes here. And then it includes giant molecular clouds and just molecular clouds in general, where things get cold enough where you can actually get molecules forming and surviving. And the way I want to end this, those are our three primary types of nebulae that we'll talk about with the ISM. I just want to share some of the images of nebulae. So here we have the Lagoon Nebula. I'm sorry, that should actually be M8, the Lagoon, or is it M20? Can't remember my Messier objects right now, so don't pay attention to that. This is Lagoon Nebula. You can see that it's primarily an emission nebula, and you can see lots of that hydrogen alpha light coming off of it, but you can still see all these dark nebulae, these dust clouds that are there. One of the most famous images in all of astronomy, because it's just absolutely stunning. These are called the Pillars of Creation in the Eagle Nebula. So here you can see these pillars that look like pillars because we see extinction of light due to dust. So these are dark nebulae. They're also molecular clouds, and stars are being born out of these pillars of creation. We have taken image of these over 2 decades, and we can see morphological, how they look has changed as the stars are born and are changing, eroding away some of the dark nebulae parts. Up here, you can see light bleeding out of this dense region up here. There is a star that has been born, a hot O or B type star, and you can see the light bleeding out. These pillars are several light years tall, and this is several light years across. I think this pillar is something like 15 light years tall. So, absolutely stunning, beautiful images. We can look at it in the infrared, so we can start peering through the dust. And now you can see where we have the densest knots, and where we have the densest knots within this, that's where we're going to get star formation. So you can see up here where we can see starlight bleeding out. You can see some starlight bleeding out of this, the tip of this pillar as well, and it's very, very dense there. And you can see all the reddening of the stars as well. So what does if we could just look and really intensify the light, just to show you that the ISM is not just empty space. Here is Orion with a very long exposure photograph. You might not be able to recognize Orion here, but you can see the entire Orion molecular cloud complex. You can see this huge emission region. And here you can see some emission nebulae, and here's some other nebulae. See some reflection nebulae in there. There's a dark nebula within an emission nebula. Here's an emission nebula over here. But you might not be able to pick out that this is Orion's belt and this is Betelgeuse down here. So let's put some lines. There is Orion. So if our eye was sensitive enough to see this faint light that you can capture with a camera, and you don't need really fancy equipment, you just need patience and someone that can track the sky, and you can get an image like this for yourself. This is all the stuff in the ISM. You can physically see the stuff between the stars. And look how absolutely enormous that is. If you haven't looked at Orion recently, Orion's a winter constellation, so you're in luck. You can go outside and you can see it. Orion is huge. It's a huge patch of the sky. So this is an absolutely enormous molecular cloud complex. In fact, within it, you can find what's called the Horsehead Nebula. So you can see the Horsehead Nebula is a dark nebula, and it's in front of an emission nebula. And why do we call it the Horsehead Nebula? Well, because that looks like a little horsey, doesn't it? Looks like a chess piece, a knight. So here we have the Horsehead Nebula, which looks like a horse head because it's a dark nebula and is blocking all the light from the emission nebula behind it. And here we have the Flame Nebula. We can look at the Horsehead Nebula up close and in the infrared, and whoo, that looks super duper cool. You can see the thinner regions where you can only see like the ghostly outline of the nebula, and then you can see these thicker regions, more dense regions, where you can get all sorts of amazing star formation, entire planetary systems being born along with the newly born stars. Here is a very famous one, the Westerlund 2 nebula and star cluster. So here's a newly formed star cluster that formed from all the gas and dust from the Westerlund 2 nebula. And you can see pretty much every type of nebula I was talking about: emission nebulae, reflection nebulae. Look at all these pillars of dark nebulae. Just absolutely stunning images, and a freshly born, newly made cluster of stars. These are NGC 2014 and NGC 2020. These are in the Large Magellanic Cloud, a satellite galaxy, and just beautiful, stunning images of the ISM. The Heart Nebula, named for very obvious reasons. And here you can see emission parts, dark nebulae parts, and reflection parts. And I want to leave you with one of my favorites. This is within the Carina Nebula. This is called the Mystic Mountain because it looks like a pretty mystic mountain, similar to the Pillars of Creation, but it just looks different. This is a giant molecular cloud. You can see these sort of materials here that are jetting out to the side. These are called Herbig-Haro objects. They are a hallmark how we can say, hey, there's a star forming right there. And in star formation, they create these jets where they shoot material out of the magnetic poles of the forming star. So you can see the effects of star formation there. And you can see all of the reflection parts, emission parts, dark nebulae parts. I wish I could show you endless images of nebulae. It's one of my favorite things. Hopefully you've enjoyed taking a step back and looking at some pretty pictures. I've also, on the README for week 11, I have put a link to the Hubble site's image gallery of nebulae. So go crazy on there. If you haven't got enough looks at nebulae yet, hopefully you can go and you can look at all of them and see nebulae to your heart's content. I will see you in the last video of the ISM.